Hi folks, this is part 6 of a playlist about the preparation of carboxylic acids. In this video I'm going to show you examples of the carbonylation of alcohols and organic halides, or in other words, the conversion of organic electrophiles into carboxylic acids by treatment with carbon monoxide. Such reactions are important for the large-scale industrial manufacture of acetic and formic acid, but can also be used for structurally more complex acids. Carbon monoxide is highly toxic, and a number of reagents have been found that can be used as safer substitutes. These include formic acid derivatives, some acyl chlorides, glycerol, oxalic acid derivatives, and molybdenum or tungsten carbonyls. Reactions with these reagents, however, will usually also generate gaseous carbon monoxide and should only be conducted in efficient hoods. One strategy to convert alcohols, halides or other electrophiles into carboxylic acids is by generating a carbocation under acidic conditions. Addition of carbon monoxide to the carbocation yields an acylium cation, which can then react with water or other nucleophiles. Some carbocations may of course rearrange, and if the cation is well stabilized, reaction with carbon monoxide will be slow. Nevertheless, many successful examples of this strategy have been reported. Cyclohexanol is a problematic starting material because the cyclohexyl cation readily rearranges. In this example, conducted in concentrated sulfuric acid, only the acid resulting from this rearranged cation was obtained. The cyclohexyl cation underwent ring contraction and hydride migration to a more stable tertiary cation, as sketched here. The cyclohexyl cation can, however, be carbonylated without rearrangement. Here, for instance, with a mixture of triflic acid, methanol and a palladium catalyst, a high yield of methyl cyclohexane carboxylate resulted. The 1-adamantyl cation is stable and does not rearrange. Actually, adamantane can be prepared by acid-catalyzed rearrangement of the hydrogenated dimer of cyclopentadiene, which is an isomer of adamantane. In this example, the adamantyl cation was formed by hydride abstraction from adamantane with the terz-butyl cation. Carbon monoxide was generated by dehydration of formic acid. Along with adamantane 1-carboxylic acid, also pivallic acid was obtained by carbonylation of terz-butanol. Despite the excess of reagents, no twofold carbonylation of adamantane occurred. Acyl chlorides can be prepared directly by radical chlorocarbonylation of hydrocarbons with oxalyl chloride. Because the energy difference between a tertiary and a secondary carbon-centered radical is much smaller than the energy difference between a tertiary and a secondary carbocation, such radical carbonylations proceed with lower regioselectivity than ionic carbonylations. In this example, the radical chlorocarbonylation of adamantane yielded a mixture of two isomeric acyl chlorides. As alternative to acid-catalyzed carbonylations, such reactions can also be run under alkaline or neutral conditions. A number of organometallic intermediates react with carbon monoxide to yield relatively stable acyl complexes. In the presence of nucleophiles, these can be transformed into carboxylic acid derivatives, as shown here. Examples of such reactions have been reported for copper, cobalt, nickel, palladium, rhodium, ruthenium, tungsten and molybdenum. Also polar organometallics react with carbon monoxide, but the resulting intermediates are less stable than transition metal acyl complexes. Because the lithium-oxygen or magnesium-oxygen bonds are so strong, these intermediates show carbene-like reactivity and tend to dimerize. By the way, these intermediates can also be generated by treating non-enolizable aldehydes at low temperature with LDA or other strong bases. Thus, treatment of organolithium or Grignard reagents with carbon monoxide mostly yields alpha-hydroxy or other ketones by the mechanisms sketched here. For instance, carbonylation of phenyllithium at room temperature gave a useless mixture of mostly 5 products. But fortunately, transition metal acyl complexes do not dimerize and are valuable intermediates for preparing carboxylic acids. Here, cyclohexanol was carbonylated in high yield by strong heating with a nickel-phosphine complex and carbon monoxide. With 2-phenylethanol, however, a mixture of two isomeric acids was obtained. Allylic alcohols undergo CO bond cleavage more readily than saturated aliphatic alcohols. Here, prenol was carbonylated in high yield by treatment with pressurized carbon monoxide, triethylamine, and acetic anhydride. The reaction was catalyzed by only 0.1% of a palladium triphenylphosphine complex, and 14% of a double bond isomer was also formed. Let's now have a look at the carbonylation of organic halides. Just a reminder, palladium or nickel catalyzed carboxylations with carbon dioxide require stoichiometric amounts of a reducing agent to regenerate the catalyst. Carbonylations, however, proceed by intermediate formation of an acyl complex, and reaction of the latter with nucleophiles yields a carboxylic acid derivative and palladium or nickel 0. Thus, these reactions are truly catalytic, and no additional reducing agent is necessary. Instead of gaseous carbon monoxide, formic acid esters or other formic acid derivatives can also act as carbonylating reagent. This here is a typical example of palladium-catalyzed carbonylation of an aryl bromide. The reaction conditions were slightly basic and heating was required. Because of the cyano group, generation of an organolithium or magnesium intermediate, followed by carboxylation with CO2, was less convenient than the carbonylation strategy. In this example, instead of carbon monoxide, potassium formate was used, together with a bulky palladium phosphine complex. A high yield of benzoic acid resulted, without any decarbonylation of the aromatic aldehyde. Benzaldehydes and acyl halides sometimes decarbonylate when heated with palladium 0 or other transition metals, but this did not occur here. Heating butyryl chloride with palladium 0 complexes can cause its fragmentation into hydrogen chloride, carbon monoxide, and propene. Here, butyryl chloride was used as carbon monoxide source for the carbonylation of 4-bromostyrene. The vinyl group remained unchanged. Also, benzyl halides can be carbonylated to aryl acetic acids, as shown here. Supported palladium and a phase transfer catalyst were sufficient to effect the benzylic carbonylation, without simultaneous carbonylation of the aryl bromide. Allylic halides are similarly reactive as benzylic halides. Here, cinnamyl chloride was carbonylated with just 0.1% of palladium acetate, without any phosphine. Under these conditions, palladium 2 was probably reduced to palladium black by the amine. Still, although this form of palladium has only moderate catalytic activity, it was sufficient for this preparation to succeed. Alkyl halides tend to eliminate hydrogen halide and yield alkenes upon treatment with nickel or palladium 0 complexes. Here it was possible to carbonylate 1-chlorobutane with the aid of a manganese complex. The target ester was obtained in excellent yield. In this example, a secondary alkyl bromide could be carbonylated with 5% of a palladium carbene complex. Cyclohexyl bromides undergo elimination easily, but still an acceptable yield was obtained here. Also, epoxides can sometimes be carbonylated. In this example, the reaction was catalyzed by cobalt bromide and elemental manganese as reducing agent. Vinyl tosylates can be prepared from ketones and may then be carbonylated to acrylic acid derivatives. Here, a substituted cyclohexanone was first converted into a mixture of two isomeric vinyl tosylates and then treated with an excess of phenyl formate and 4% of a palladium catalyst. A low yield of the target ester was obtained without any epimerization or transesterification. Alkenes and alkynes can be converted into carboxylic acid derivatives by treatment with carbon monoxide and palladium or nickel catalysts. The first step is the reversal of a palladium-induced beta elimination of the halide. In other words, a palladium hydride generated from palladium 0 and the hydrogen halide adds to the alkene. Carbon monoxide insertion then yields an acyl palladium complex, which can react with nucleophiles to the acid derivative and palladium 0. This here is an example of such an olefin carbonylation. Only 1% of a palladium carbene complex, together with pressurized carbon monoxide, was enough to convert the starting ethanol completely into a mixture of two ethyl esters. No acid or base was required. Alkynes behave similarly. In this instance, in addition to a palladium phosphine complex, 2% of triflic acid was used to catalyze the reaction. No carbonylation of the aryl bromide occurred, because aromatic carbonylations usually require alkaline conditions to cleave the hydrogen halide from palladium and thus regenerate the catalyst. When palladium-catalyzed alkene carbonylations are conducted in the presence of an additional oxidant, twofold carbonylations can occur. The first step of such reactions is similar to the Wacker process, with carbon monoxide instead of water being the nucleophile, as is sketched here. As in the Wacker process, palladium-2 must be regenerated by oxidation of palladium-0. Here's one of the few examples reported. Treatment of cyclopentene with carbon monoxide, air and a number of further additives gave a high yield of a mixture of two isomeric cyclopentane dicarboxylic esters. The reaction was not very general though, and with styrene for instance only a low yield of diester resulted. In this example, chloroform was used as synthetic equivalent of gaseous carbon monoxide. Trichloromethylation of a substituted furane proceeded by intermediate radicals, but still with high regioselectivity. This is another example of oxidative alkoxycarbonylation, of a substituted benzaldehyde in this case. Oxalate was the carbon monoxide source. Unfortunately, stoichiometric quantities of silver carbonate and a large amount of an aniline were required, making this procedure uneconomic. Anyway, it's good to know that such a reaction can work at all. What about potential side reactions? In addition to acid or transition metal catalyzed double bond or other isomerizations, carbonylations often proceed twice and yield alpha-keto acid derivatives, as in the example shown here. These ketones are often formed in small quantities only, and it can require a lot of optimization to suppress or minimize this byproduct. Then, alcohols can also add to carbon monoxide and yield alkyl oxalates or carbonates. These may complicate the purification of the target product. Carbon monoxide is also a good reducing agent. In this example, a nitroarene was reduced by formic acid and 0.5% of a palladium catalyst. In this instance, if the aryl bromide was to be converted into benzoic acid, carboxylation would be more promising. Here are some further references which you can also find in the description of this video. For subscribers, there's a PDF version of this presentation under the Community tab. The next video of this playlist is about the hydrolysis of various carboxylic acid derivatives, for instance esters and amides. These are the most common reactions both in laboratories and in the chemical industry, and a huge number of examples have been reported. I'll show you difficult cases and some newer strategies. So long!